Hi everyone, in this video we're going to be looking at applications of exponential functions. So I'm going to go through a few situations here where we're going to see exponential functions in a kind of more practical situation, and I'm going to do a couple of examples. So here's a really basic one where we've got cells dividing, and we've got so start off with one cell at time 0 weeks. After 1 week we've got 2 cells. After 2 weeks we've got 4 cells, and they keep dividing in that kind of fashion. So here we want to come up with some equations that model this situation. So if you have a look in the table here, I could start filling the table and say, oh, okay, it's doubling each week. That's really what's going on. Okay, so what's the equation that describes this situation? So we want an equation in terms of the number of cells and involves t, the number of weeks. Well, in this case it's an exponential equation. And if I just say 2 to the power of t, that is the correct equation. And you can just check that. 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 cubed is 8, etc. So that is the correct equation that models that basic situation there. So we can then, once we have the equation, we can then answer questions. How long does it take for there to be 100 cells present? So if we've got the equation that the number of cells is 2 to the power of t, we can then solve the equation 100 equals 2 to the power of t. And this is where I'd get out my calculator in the calculator section, and it would give me a value of t. You won't be expected to solve things like that using other techniques. And you could go on and do part B. How long does it take to be 400 cells present? So I would just change this to 400. And we've done C, the rule for C in terms of T. Okay, let's try some other situations. An investment of $500 earning interest of 10% compounded annually. We've got a graph over here that shows us what's going on. So we start off with $500, we're adding on 10% and just compound it annually. So this is compound interest, so we're not only earning 10% of our original investment, which gives us $550 for the next year, but for the next year we're also earning interest on the interest we've earned. So we add another 10% onto $550, and so on and so on. One way that I like to think about this is, here's a percentage scale, here's 100% in the middle, 100% of the cost of something, the value of something. If we add on 10%, which is what we're doing here, we end up calculating 110% of the original value, which as a decimal is 1.1. So adding 10% on is the equivalent of timesing by 1.1. Similarly, if we're going down, if we're decreasing, so let's say I have a sale and it's a 20% off sale. If we take 20% off 100%, I end up down at 80%, which as a decimal is 0.8. So if we're taking 20% off the price of something, that's the equivalent of timesing by 0.8. This kind of concept is going to be really helpful when we do these problems here. Okay, so in this case here, I'm going to come up with the equation for the value in terms of t. So how much money have we got after t years? In this case here, the value of our money is, we start off with $500. I'm going to put that at the front, and you can see after 1 year I've times by 1.1, so that gives me $550 after 1 year. For the second year, I take that amount of money that I've got and I times it by 1.1 again. That's how much money I will have after 2 years. For 3 years, you can see the pattern here. I take that amount of money that I've got after 2 years and I multiply it by 1.1 again. And you can see the pattern building up. So after 3 years, I've got 500 times 1.1 cubed. So I'm going to make this a bit simpler and coming up with a formula now. The value is just 500 times 1.1 to the power of t, where t is the number of years that I've got that money in the bank. Now once I've got that little equation there, I can now start to answer questions like, how much money will I have after 20 years? When will the amount of money I have in the bank reach 1,000, 10,000, $1 million, those kinds of things. So we can now start to answer those questions once we've come up with the equation. Okay, situation 3. We've got a culture of bacteria, initial population of 100 cells, and the amount is doubling every hour. So this is kind of similar to our last one that we had, except in this case here we're starting off with 100 cells. So I'm going to say that the population is starting off at 100 and we're doubling here. So that's how much we'll have after 1. How much will we have after 2 hours? We'll have that amount times 2 again. After 3 hours, etc. You can see the same kind of thing going on here. Our formula is 100 times 2 to the power of t. Okay, situation 4. We've got a car, it costs $40,000. It's decreasing in value by 12%. And that happens every year. So you can see from the graph here that the value of the car is going down. So remember what I said about this line here. We've got 100% of the value of the car when we first bought it. If it decreases by 12%, we're subtracting off 12% from 100%, which leaves us at 88%, or as a decimal, 0.88. That's where we get this model from. You've got your initial value here, times by 0.88 to the power of t. And that will give you the value of the car after t years. Situation 5, again we're decreasing here. It's a radioactive element and it's decaying at the rate that sees 40% of the element decay to a more stable form each hour. So we're subtracting 40% off each time. In other words, we're multiplying by 0.6 each time to go from here to here. Remembering the scale, here's 100%. We're minusing off 40% every time. So this takes us down to working out 60% of the original each time, or timesing by 0.6. So we start off with 500, timesing by 0.6 each time. That gives us that rule there, and you can see from the graph that we're decreasing. So we start off here at 500 and we get this exponential decay curve, if you like. Notice as t gets really, really, really big, that the value is tending towards 0. So we can see when you've got 0.6 to the power of a really, really, really big number, that's really, really close to 0. Okay, so there's some situations that involve those exponential functions in a real life situation. I'm going to do a few problems now that are going to help us to do questions similar to what we might expect in a test on this. So let's do this one, example 1. This population is growing exponentially. Populations in each of those 4 years are given. Predict the population of this country for the year 2030. So I'm going to come up with a relationship here. First thing that I might want to know is by what percentage is the population growing from year to year. For this exponential model to work, we need that population growth to be regular each time. So it's increasing by the same amount each time. So let's look at what the percentage increase has been. If we go from 20 million to 20.4 million, that is a 0.4 million change over our original 20 times 100. That's the formula for percentage change. It's the change over the original amount and then times by 100 to convert it to a percentage. So that's around about 2% if you work that out on your calculator. If you do the same thing from 20.4 to 20.81, again you get something very close to 2%. And if you calculate the percentage change between these two, you get 1.97%. So again, all of the growth rates are very close to 2%. So this is the way I'm thinking. If we're 100% here, if we add on 2% to 100% each time, we're calculating 102% of the original. Or if we're doing a calculation, we're timesing by 1.02 each time to get the next one. So that's another way of doing this, is you could just compare the ratios of the numbers. So you could just go 20.4 divided by 20. that's exactly 1.02. You could then do 20.81 divided by 20.4. Look at the ratio of those two. It's about 1.0201. And then the last one, which is 21.22 million divided by 20.81, and that is around about 1.0197. So you can see in each case we're pretty close to a 2% increase. So if you work backwards from that 1.02, oh, that's a 2% increase. Okay. So now we've established that we're increasing by around about the same rate each time, and you might get a question like that says, what is the average percentage increase each time that we do this? So we've established that that is around about 2%. Okay. So let's come up with an equation here. The population is going to be, now we're starting at 20 million. So I always put the 20, or the starting value at the front here, 20 times 1.02 to the power of t. So the next year we're saying 20 times 1.02 to the 1, then we're taking that value times it by 1.02 again. Okay, so the question's asking what's the population for the year 2030. So that's going to be 20 times 1.02. Now how many years is that? 2030 minus 2010. That's actually, oops, 2010. So that's actually going to be 20 years that we're doing this for. So when you do that on your calculator, 20 times 1.02 to the power of 20, you get approximately 29.7. And remember, we're talking about millions here, so about 29.7 million by the year 2030.